let's talk about how it would look to set up a triple integral in cylindrical coordinates where the dv gets replaced with r dz dr d theta. Now, this is not the only order that works, but I think this is the easiest order to at least talk about. So, step one, set up, as you might expect, the inner integral. So that's, in our case, the dz, at least based on this order. So you'd have to find, in the geometry, this is always the thing, right? So you'd have to find upper and lower bounds for z. And let's just comment that both of these bounds, they can depend on r and theta if you want. They can, of course, be constants. Okay, so given a fixed r and theta, what's the lowest and the largest value of z? Right. So the thing is, it does. Yeah, this should be based on fixed r and theta, right? Because that's what we would have done with x's and y's, and so in some sense morally you can almost think about it like, because it's x and y that determine r and theta, you could almost say, this is almost just thought of as fixed x and y, but you really do need to be thinking about r's and thetas. Okay, so in terms of a picture, you'd have maybe something like this. So let's get our x, y, and z axes here, and there is some object, which I'm gonna just try to draw some three-dimensional blobby thing here called E, and maybe it looks a bit like a tank or a pill or something like this. And then the point is for a specific value of xy, but it's really a value of r and theta. So maybe there's like a point right here, and it's described. So this point on the xy plane is described in terms of r and theta. And what you do is you move up until boom, you end up hitting the object, and then you're inside the object. And then at some point right at that moment, let's say you leave the object, and so you're trying to get the lower z value and upper z value all in terms of r and theta here. Once you've done that, step two, you project to the xy plane. Yeah, so the object that you have just a moment ago above, I'm going to redraw the picture instead of drawing on top of the existing picture. So you have, here's my attempt at trying to draw the same picture. I think this will be good for your own notes if you also work on redrawing a picture. So there's like a R2D2 like top to this thing. This is not just meant to be a can or something. But then we look at the shadow of this thing down here, and it creates maybe this shape. Okay, this thingy down here. And let's call that region D. And then let's just draw that in two-dimensional space. So maybe it looks like, okay, this does look a little taller in the y direction than it is. It looks a little taller than wide, so I'm going to try to draw just sort of roughly an attempt of the same picture here. Then, step three is looking at this picture over here, we should find, now just going back to our integration order, r is next, so we should find upper and lower bounds for r, okay, looking at this projected picture here. Okay. Now, these bounds can depend on theta, right? So because that's going to be the outside integral. So the idea here is I'm going to redraw this picture without shading it in. What you should be doing is in the xy plane, so you've got this projected object here. So for a fixed value of theta, maybe like this, so theta looks like that. For that fixed value of theta, you should be getting, oh yeah, now we're in the object, now we're outside the object again, right? So you want to know what's the value of r here as a function of theta, and then what's the value of r here as a function of theta. Finally, it's kind of weird then at this point to say that you want to project away r because, well, there's no r axis, right? So then what you have to do, it's a little different, but you have to find your bounds for theta by what I would like to call sweeping. Okay, you're just trying to find, again, constants, right? So at this point, these must be constants. And how do you find the lowest and largest values of theta? Again, trying to use the same picture. What you do with this object is you keep drawing in small values of theta and then look at larger values of theta until, boom, you just hit the object right at that moment. And you just keep doing this until the very last ray of this kind where you leave the object. So this ray, those are the important ones. Maybe I'll star those. But just to keep going, you just sweep around rotationally. So for the first moment that you hit the object, okay, that's your starting theta. That goes here. And then the last moment you leave the object, that's your next value of theta. All right, let's actually try this process. Yeah, so let's just full on do an example here. I'd like to find the volume of the solid. Let's name the solid E, enclosed by the cylinder x squared plus y squared is equal to 4. Okay, so radius 2 cylinder, right? Bounded above by the paraboloid. Z equals x squared plus y squared. Let's write that a little cleaner. Just this is getting in the way here. Z is equal to x squared plus y squared, and below by the bounded below by the xy plane. Okay, now just to get us started here, we're talking about finding a volume, and so because we're talking about finding a volume, the function f that we're going to integrate is just equal to 1. What I mean is, let's just clear this up a little more. So f of x comma y comma z is equal to 1. We could be asked to integrate some other function as well. It doesn't have to be 1, but because we're finding a volume, we have 1 here. If we could have just been asked to set up an integral for an unknown function or something like that. Let's draw a picture. Okay, so what we have going on is there's this cylinder. So first of all, right, like that looks like this. Well, let's try get these to look even. Okay, so something, like now the lowest circle we have, because of this bounded below by the xy plane, should be right here. Okay, but then above it, there's a paraboloid, right? So that's just basically take a standard parabola and you spin it around, and so then below this paraboloid, but above this circle here, so there's this kind of region that's shaded like this. It's almost like if you took a tube that's just filled with Play-Doh and then you pushed in a shape like roughly speaking, a dull pencil or something inside, and it just kind of squished and packed the Play-Doh in or something like this. Okay, so that's my attempt of trying to describe it. These things tend to be hard to draw. I apologize for that. If we're going to go with that order of r dz dr d theta, then we need bounds for z first, right? So we're going to, just to outline the order here, we should find out what's the smallest z and largest z, and z can be written in terms of r's and thetas. Okay, so so for a fixed r and theta, we see that, and we'll do this in a new color here, but we kind of come through and boom, we end up hitting right at the bottom of this circle where z is equal to 0, and then we're inside the shaded object until at some point we end up hitting the paraboloid, excuse me, and then we end up leaving the shaded object. So this looks to me like we should have 0 less than or equal to z less than or equal to x squared plus y squared, because that's the equation that defines the paraboloid. But we can't do this. Okay, we can't have here x squared plus y squared. We have to do things in terms of r's and thetas. So we just replace this x squared plus y squared instead with an r squared. Okay, so those will be our bounds for the z integral, right? So we set up, let's just, hold on to that. Then we're going to project. So if you take the points that are here and you project them down onto the xy plane, what you will have is, due to this circle of radius 2, right, you'll have here projected, you're going to have a filled in circle of radius 2. Okay, so then we need to describe this. We could do this in x's and y's, but we're trying to practice the cylindrical coordinates thing. So here, just like with, we would describe this the same way in polar. It'd be r between 0 and 2, and theta between 0 and 2 pi. So in setting up an integral, the volume of this shape E that we're trying to integrate over, okay, it's going to be triple integral over E of 1 dv. But if we really implement and write out what we have here, we're going to be talking about integral, leave a little space, integral, leave a little space, integral, just so we can write the endpoints of integration on it. We're doing the function 1 here, but we could have changed that to whatever other function we would have been requested. And then the dv right here turns into r dz dr d theta. And since the z is on the inside, scrolling back up, we had up here 0 to r squared, and then r is the middle integral, 0 to 2 as we see right here, and then theta goes from 0 to 2 pi as we see here. The integral is set up. Now it's really, the challenging work has already been done. If we start to do some integration here, why not? So we're trying to integrate the function 1 times r, or in other words r, with respect to z. Yeah, so it's 0 to 2 pi, 0 to 2, so this will be rz, where z we have to plug in 0, and for z we have to plug in r squared, dr d theta. And then we'll clean that up here, 0 to 2 pi, integral 0 to 2. Plugging in 0 is going to mean we don't really get anything here, so plug in r squared. We end up with r cubed. So we just need to integrate r cubed dr d theta. So 0 to 2 pi, let's see, r to the 4th over 4, and we're plugging in r is equal to 2 and plugging in r is equal to 0 d theta. So integral 0 to 2 pi, let's see, 2 to the 4th, 16, right? Over 4 d theta, and this should in the end turn into 4 times 2 pi.